This is the first lecture on the root locus analysis method or technique. It is found in Ogata's Modern Control Engineering textbook, Chapter 6, at least for Edition 4. And this first lesson is just going to introduce the idea of the root locus, the big picture, and then we'll have a separate lecture or Part B lecture that will present the actual steps to applying or generating the root locus plot. So root locus analysis was developed by Walter Evans in 1948, and so we just want to give some recognition to the inventor here. Our outline from the textbook is that we're going to give an introduction. We'll then show how to generate the plots through some examples, and then kind of go back through it, but formalize or summarize the general rules for constructing the root locus plot. Look at using MATLAB to assist in making root locus plots, and then there's some special conditions or situations in feedback systems that we'll want to look at, such as positive feedback, conditionally stable systems, and systems that have a transport lag, a delay. Okay, the outline then for our class time is we're here, week 11, and so I want you to be following along in the textbook. So this first lesson, we're going to look at section 6.1 and 6.2. In all, we will spend 6 classes. The next chapter, chapter 7, actually is focused on designing our feedback control system design using root locus method. And so we will apply the root locus method in some system designs in the following chapter. Okay, so what is the root locus method? So this analysis technique gives the designer insight into how the closed loop system poles move in the S-plane in response to a change in open loop gain. So a lot of times there is a constant K. We've seen that with like a proportional controller, an integral controller, and we've seen that the closed loop poles, think of a servo system now with perhaps just a proportional controller, constant K or Kp, we found that the actual damping ratio, zeta, was a function of that constant. So changing that constant actually results in the closed loop poles of the system moving. Okay, since the location of the poles determine the nature of the system response, including its stability, knowing how poles move, including which direction and along what trajectory, can be important. In other words, we can gain insight into how changing a gain parameter actually moves or displaces the poles, and in which direction. For instance, are they going toward the j omega axis? Are they going further into the left half S-plane? These we've seen impact whether a pole is a dominant pole in the system, and therefore whether the system is going to have a fast or a slow settling time, whether it will be underdamped or overdamped, etc. So although the root locus plot can be effortlessly generated using MATLAB, developing skill to plot a root locus manually leads to a better understanding of how open loop gain is linked to the closed loop poles of the system, and can thus, I didn't finish my sentence. Okay. It can thus guide us as to where we should place our compensator poles. Okay, so again, so far we've looked at just P, I, and D compensator or controllers, and essentially there we are placing poles and zeros on the S-plane and adding them to our open loop transfer function. And the question is, what would be helpful if I'm wanting to achieve a particular type of response? What should I add? Should I add a pole? Should I add a zero? And where should it be on the S-plane? The root locus method will give us insight. A lot of times that's qualitative. We won't look for the root locus to give us exact quantitative results, because at that point it's easy to use a computer program to help us. But in a problem where the solution space is really wide open, right, and we can put a compensator in our system that has poles and zeros anywhere, and how do we narrow that down judiciously, thoughtfully, without having to just entrust everything to a computer, just doing trial and error. So that's what the root locus is really about. Okay, so before we go into the technique, let's just look at two preliminary examples, ones that we've already seen, but now we're going to look at them from the perspective of root locus, and you'll see here what a root locus is, because I haven't yet defined it. So consider this first order system, 1 over st plus 1. T would be a time constant, and we're going to add a proportional controller, k. Closed loop gain is forward gain over 1 plus the loop gain, which simplifies to this transfer function that has in the denominator st plus the constant 1 plus k. And so our pole to our system is actually at minus the quantity 1 plus k over our time constant t. So we see here how we see that changing k actually moves this pole, and so we want to draw on the S-plane here how that pole moves. So what we're going to look at is the range of values of k between 0 and k equal to infinity. We're going to assume that it's positive. Note that if we let k go negative, then our loop gain is we no longer have negative feedback, because if you walk around the whole loop, there will be a minus sign here, and then we'd have another minus sign due to the k, and so that would be a positive feedback system, which would result in not only the pole being to the right half of the S-plane, but that would mean then that our response c of t would be an e to the positive coefficient times time. So if we set k to be equal to 0 here, we end up with just st plus 1 in the denominator, and our pole would be at minus 1 over capital T. We see that just by plugging in k equal to 0. Now that's not very useful, because we've actually broken the feedback loop. If you have k equal to 0, there is no way for the reference signal to get in. However, it's still true that our response c of t is due to a system 1 over st plus 1, and thus, if there was an initial condition on that system, we would see it decay according to a time constant of capital T, or a pole of minus 1 over t right here. Now as we increase k, the value of this pole will move to the left. So if k was equal to 1, then the pole would be at minus 2 over capital T, and this would be for the case of k equal to 1. Well, you can imagine as k continues going to, oops, and this is a typo, this is a plus infinity there, k equal to plus infinity. As k goes to plus infinity, our pole goes to minus infinity. Okay. So notice, first off, something that will always be the case, at k equal to 0, the pole of our system, of our closed loop system, okay, this is closed loop pole, is equal to the open loop pole. Okay, that's an important concept, fact that you're going to want to remember. So the open loop pole is just when you look at this term here, which we'll call G, just k over st plus 1. the open loop, the pole to that transfer function is minus 1 over capital T. And the closed loop pole, being simply minus 1 plus k over t, evaluates to that open loop pole when k equals to 0. And then as k goes to infinity, our closed loop pole goes to minus infinity. And this is actually our open loop 0. Now, you may not recognize that at this point, because you would say, well, now wait a minute. If our open loop transfer function is k over 1, or k over s t plus 1, where is our open loop 0? We don't have any open loop 0, right? Well, let me see, open loop pole, open loop transfer function. We actually do have 0, but this 0 is at infinity. So we say that this has no finite 0, but it has 1 0 at s equal to minus infinity. So a 0 is whenever the transfer function goes to 0, which clearly happens if we have a denominator, a numerator that has something like s plus 2, right? Then we'd have a 0 at minus 2. But if there are no finite zeros, as is the case here, then the only way that the transfer function can go to 0 is when the denominator goes to infinity, which in this case is when s is equal to infinity. And there will always be a 0 for every pole of the system. Okay, so if you think about a pure integrator, 1 over s, it has a pole at s equal to 0. It has a 0 at s equal to infinity or minus infinity. If you had the transfer function of 1 over s plus 4, again, it would have a pole at minus 4, but it would have a 0 at minus infinity. So an interesting observation, which we maybe can't make a rule for it yet from this one example, but I can tell you that it is true for all cases, is that the closed loop poles start at the open loop poles and they end at the open loop zeros. And what I mean by start, it's when k is equal to 0, and by end, I mean it's when k is equal to infinity. Notice that based on this this drawing here, we can say that this system is absolutely stable. There is no value of k between 0 and infinity that would result in the system being unstable, because the locus of poles is always in the left half s-plane. Okay, and so this whole thing here, this is called the root locus. It's the locus of roots of the denominator as we vary this parameter k, this gain in our system. I should mention that in general you can vary any one of a number of parameters in your system, though oftentimes it will be simply a k that would be in the numerator of your controller, such as kp or ki over s or kd times s, those kind of terms. Now let's consider the same first order system, but now we have added a integrator controller, k over s. So our transfer function, our closed loop transfer function, is going to be k over s squared t plus s plus t. And if we put it in standard form, we can find that It has a damping ratio that is equal to 1/2 times 1 over root of kt, and a natural frequency of square root of k over t, leading to 2 poles, and we can write those in terms of omega n and zeta, which we often do. In this case, however, it's going to be more useful to return to the original non-standard quadratic expression and solve for the roots directly there. And we find that the roots are minus 1 over 2t plus or minus 1 over 2t times the root of 1 minus 4kt. So we have 2 cases. One is going to be when k is greater than or equal to 1 over 4t. In this case, we will have complex conjugate roots and an underdamped system. And when k is between 0 and 1 over 4t, we'll have an overdamped system. Notice that the real part of our poles, minus 2 over t, is constant for the underdamped case. And what that leads to is a root locus that, for an underdamped case, will follow a vertical path rising from the s equal to minus 1 over 2t. And the point of departure here is going to be when k is equal to 1 over 4t. When k is less than 1 over 4t, then the poles lie on the real axis. And in fact, they begin, if we look at this expression here for the overdamped case, if we set k equal to 0, then we have roots at minus 1 over 2t plus or minus 1 over 2t square root of 1. So in other words, we have minus 1 over t and we have 0. So this corresponds here, this pole at 0 corresponds to the case of k equal to 0. This pole at minus 1 over capital T corresponds to the case where k is equal to 0. And as k goes to infinity, the poles become first complex conjugates, and they then move to plus j infinity and minus j infinity. So this shows the locus of points on the S-plane where the closed loop poles of this system could lie as a function of k. And we see that for small k, the system will be overdamped, and it will remain overdamped until k equals 1 over 4t, at which point the roots or the poles become complex conjugate. However, we see that the root locus always runs vertical and never moves toward the j omega axis, and so the system does not become less stable, and it certainly does not become unstable. So we can see that this system is absolutely stable. It's absolutely stable for, and we'll have to qualify this, for k greater than 0. And the reason for that is that at k equal to 0, we have one of the poles is going to be equal to 0, and the other one will be equal to minus 1 over capital T. And so this pole at 0 results in a critically damped system, not an absolutely damped system. Okay, so the technique, the root locus technique that we're going to learn, is going to allow us to through a manual, non-computerized procedure, be able to sketch initially, qualitatively, but to varying degrees quantitatively, the locus of roots on the S-plane, and including knowing whether or not that locus of points could land us in the right half S-plane, and thereby produce an unstable system. So now let's look at the basic principle before we develop the tools or the steps. So we have a system whose open loop, in this case the open loop's gain, is G of S, and our closed loop gain, say G closed loop, is C over R, and it's going to be equal to G over 1 plus G. So the system, the stability of the system, is determined by the poles of the transfer function, and these are determined by the roots of the denominator, specifically the roots of 1 plus GS. And that is to say that the roots, or the poles of the closed loop system, will be found by satisfying the condition that G of S is equal to -1. This yields the system poles. This is not new, but it's just a different way of looking at it. So G of S equal to -1 comprises two requirements. One is that if we express G of S in polar form, we have a magnitude requirement and we have an angle requirement. So wherever there is a pole, at that value of S, G of S should have a magnitude of 1 and an angle of either 180 or some multiple of 180 plus or minus n times 360. Okay, so anything that lands us on pointing on the negative real axis. So we can write that as having an angle of plus or minus 180 times 2n plus 1, where n is 0, 1, 2, 3, etc. Okay, so we now want to look at the particular form of GS and see where this new means of determining the closed loop poles can lead us, mainly finding where G of S, the open loop transfer function, has a magnitude of 1 and an angle of 180 degrees. So we've seen this form for a transfer function before, but remember, this is the open loop, not closed loop. This is the open loop transfer function. Let's say that it's in this form, k times a factored form of zeros over a factored form of poles. And let's be clear that k is going to be a non-negative constant. Now in this case, k represents some gain constant in the system. This typically will arise from the controller. So for instance, if our controller is a PID controller, we could have a k that multiplies all of the terms, or in this case it'd be a multiplying, I guess, all of them. And so k would be the quantity that we'd be looking to vary in this case, and to study its impact on the closed loop poles. So in general, it should be noted that the root locus method can be extended to include any system parameter. So you're not stuck with just varying this particular k that's in this location, our transfer function. But we will limit ourselves for now to a k that's in this, that scales the entire open loop G of S. Okay, so the goal is to determine how the closed loop poles of the system respond or move in response to k being varied. And doing this based on the open loop gain or G times H in a non-unity feedback system. And notice that the important point here is that we never have to directly find the closed loop poles from factoring 1 plus G of S is equal to 0. We're going to find the closed loop poles by simply looking at the open loop transfer function G of S and looking for when it has a value of -1. In other words, a magnitude of 1 and an angle of 180 degrees. So given G of S of the form stated here, the roots of 1 plus G of S are given by magnitude of G of S equal to 1, and then the angle of G of S equal, again, to this plus or minus 180 times 2n plus 1, where n is a positive or non-negative integer. So we need to satisfy the magnitude and the angle condition. So now, by satisfying the angle condition, we find the locus of points on the S-plane that map out the movement of the system poles as k is varied. For any point on this locus, the magnitude condition can be satisfied by appropriately choosing k. And here, if we know that the magnitude, let's see, if the magnitude is equal to 1, then we're saying that the magnitude of S plus Z1 times S plus Z2, etc., over S plus P1 dot dot dot, okay, is also equal to 1. Oh, and with the k out front. And so we can solve for k by simply taking the reciprocal of that. So what's significant about this is that we can actually find the locus of closed loop poles by actually just studying the angle condition and not the magnitude condition. So pretty much everything we're going to focus on here for generating this root locus plot is going to be based on looking at satisfying the angle condition, G of S equal to this plus or minus 180 times 2n plus 1. And only as a follow-on operation or step would we actually find the value of k at one or at multiple points along that root locus. The angle of G of S is expressed as the sum of all of the zeros minus all of the angles of the poles of the transfer function. So here we have phi1 is the angle of S plus Z1. So I'm going back and we're actually looking at this right here. Okay, so angle of G of S is going to be angle of S plus Z1 plus angle of S plus Z2, etc., minus all the angle contributions from the denominator. So that's S plus P1 plus the angle of S plus P2, etc. And those are being called phi and n. So phi for the angles of the zeros and theta for the angles of the poles. So now let's look at this a little closer and see if we can graphically picture what these angles phi1, phi2, theta1, theta2 are, etc. Okay, let's take a look at how we interpret or determine graphically this angle of S plus P1 or S plus Z1, etc. So let's assume that we have a pole that is located at minus P1. Note that the way that the transfer function is formatted is we have factored terms that are S plus P1, S plus P2, etc. So the poles are actually at minus P1. The zeros and minus P2, etc. The zeros are at minus C1, minus C2, etc. Okay, and now we have some S. It's just some test point on the S-plane, and we're trying to determine what is the angle of the quantity S plus P1. Okay, so first, what is P1? If we plot P1, P1 is a vector that would start at the origin and point to P1. P1 is going to be positive, right? Because we're assuming that the actual pole of minus p1 is negative here on the negative real axis. The vector s is simply a vector going from the origin pointing to our test point s. Okay, and so s plus p1 is simply taking the vector s and adding p1 to it, such that we arrive at this vector, which is s plus p1. This angle here is theta 1. But notice that this s plus p1 has the same angle as this vector that is pointing from minus p1 to s. In other words, it's simply shifted by an amount minus p1. Okay, so in the end, this angle here is also theta 1. So that means that if I have a pole at minus p1, another pole at minus p2, and I put a test charge right here, and I'm trying to evaluate what is theta 1 and theta 2 at that point, all I have to do is draw a line from minus p1 to s, from minus p2 to s, and these angles would then be theta 1 and theta 2. So let's go back to this example here and recall that the angle of g of s is going to be the sum of all of the angles of these zero terms, so s plus z1, s plus z2, etc., minus all of the pole factors, which are going to be angle of s plus p1, s plus p2, etc. And so here we can look at an example. Look at this one here, where we have two poles and a 0. We're putting a circle here for our 0. And just like for the poles, the angle s plus z1 is going to be this angle here from the horizontal, the real axis, pointing up to this vector that is joining minus z1 to our test point. And so the overall angle of our example g of s here, having a 0, z1, and two poles p1 and p2, is going to be equal to phi 1 minus theta 1 minus theta 2. And those have all been highlighted graphically on the plot here, such that this net angle could be estimated graphically. And you can try this out. If you place the test point on the negative real axis to the left of P1, you can show that the angle will actually be minus 90 degrees, which does not satisfy the 180 condition. Therefore, no root locus to the left of P1. And finally, I think I noted this before, but K does not affect the angle. So instead, what we do is we look for the locus of points on the S-plane where the angle condition is satisfied. In other words, the angle of this open loop transfer function, right? All the zero terms divided by all the pole terms, the angle of that is plus or minus 180 degrees times this 2n plus 1. And once that locus is found, positioning the closed loop poles at a particular point along the root locus is achieved by choosing K to satisfy the magnitude condition. In other words, g of s, magnitude of g of s is equal to 1. So we now are at the point where I've given you the big idea, and we will then look at a procedure for how to generate the root locus. So there are a number of steps. I won't go through them in detail now. Let me just scroll through so you can see what's coming. But we'll have another lecture where we'll work through all of these. So you're going to do things in this order. Typically, you're going to locate poles and zeros of the open loop transfer function on the S-plane, and you will mark those. You will then determine the root locus on the real axis. So if there's some zeros and poles, where is the root locus on the real axis and where is it not? In some regions there will be the root locus, in other regions it will not be there. After that, you will determine the asymptotes of the root locus. So we saw that in our second example here, the asymptotes were actually going at plus 180 degree angle and down at minus 180 degree angle. Those were the two asymptotes. All right, so if you zoom way out, you'll eventually see that basically your root locus plot is just going north and going south. Well, if you have a different number of poles, we'll see that if, for instance, you have 3 poles and no finite zeros, your root locus would look like something like this, where the asymptotes are now at 60 degrees from one another, rather than 120 degrees from each other, rather than 180 degrees from each other. So that'll be the next step. Fourth, find the breakaway points and break-in points. So just like we did on this second little example, there was a breakaway point right here at minus 1 over 2 capital T, where the root locus left the real axis and one branch went north and one went south. So we'll need to determine the breakaway points and break-in points, because sometimes the root locus will leave the real axis and then later it will actually rejoin the real axis, so that'll be called a break-in point. Next, we determine the angle of departure or arrival from or to a complex pole, complex conjugate pole. And so for instance, here's a little root locus plot where you would have some poles in here, right here, and you have a finite zero here, and the root locus actually is drawn as I've shown it here, that there's going to be one branch that's going to go on the horizontal axis and the other two basically take off. But you notice the angle of departure here is going to be important, especially when you're close to the j omega axis, because that might indicate whether or not that root locus branch is going to cross the j omega axis, or at least whether it will get close or move closer to the j omega axis, thus making the system less stable. All right, next would be find the possible j omega axis crossings. So if it turns out that your root locus plot actually takes on some asymptotes that, this is poorly drawn, but say plus 60 degrees and minus 60 degrees, at some point the locus will actually cross the j omega axis right here and right here. So at that point those two poles will be purely imaginary. For anything beyond that, like a k value greater than that, then those complex conjugate poles would have positive real parts and the system would be unstable. So we want to find where those j omega crossings are. Okay, and then we want to test a series of points in the vicinity or neighborhood of the real and imaginary axis and satisfy the angle condition graphically in that vicinity, and that will help us fill out the root locus path along with the information that would have been gathered up to this point. And at that point, you should be able to draw the root locus plot. And once you have that drawn, you can then think about either how you want to modify the root locus by adding some further zeros or poles in your compensator. Or if you can work with that particular root locus plot, then you need to decide where you want to place your actual closed loop poles on that locus of points. And then to achieve that, you have to pick the proper value of k to achieve it. So this is the big picture, and in the next lesson we'll work through these steps on how to construct the root locus plot.